Hello everyone, my name is Xingtao Zhao, and I'm a master's student at Beihang University. It's a great honor to share our team's work on uncertainty quantification for large language models. Today, I will present SeSE, or Semantic Structural Entropy, a black box framework that helps identify unreliable LLM responses and suppose abstention decisions. The QR codes provide access to our paper and open source repository, and we warmly welcome your feedback. The first part explains why uncertainty quantification is essential for trustworthy LLM systems. The starting point is a mismatch between how reliable LLMs sound and how reliable they actually are. Large language models are now widely used because of their impressive capabilities. However, even SOTA models frequently generate plausible but factually incorrect statements, commonly known as hallucinations. Alignment methods can improve helpfulness and truthfulness, but they do not eliminate this problem. More importantly, conversational LLMs often lack a reliable way to evaluate the factuality of their own responses or communicate uncertainty. Even when a model should be uncertain, it might still answer fluently and confidently. A simple example makes this mismatch concrete. Here, a user asks about the environmental impact of constructing the Eiffel Tower. The model gives a detailed answer and then claims to be 100% confident. However, the answer fails fact-checking. There is no evidence that a Parisian tiger ever existed, and the response also exaggerates the Eiffel Tower's role in the origin of green architecture. The problem is not simply that the model is wrong, it's wrong while sounding authoritative, without giving the user a useful warning. For non-experts, this combination can be especially dangerous in high-stakes domains, where an incorrect answer might lead to costly or harmful decisions. We therefore need a mechanism that identifies unreliable responses before users act on them. A promising approach is uncertainty quantification, or UQ. Given a query and a response, UQ estimates how likely that response is to be unreliable. When uncertainty is low, the system might return the answer normally. When it's high, the system can abstain when the user requests more information or escalates the case to a human expert. Uncertainty therefore becomes an actionable signal rather than only a descriptive score. For example, a robotic system might ask for human guidance before taking an uncertainty action, while a medical assistant might send a high uncertainty response for professional review. The next question is how uncertainty should be defined for open-ended large language generation. Traditional methods often treat an LLM output as an autoregressive token sequence. This makes them sensitive to lexical variation. Two responses might use different words while expressing the same meaning. For factual reliability, meaning matters more than surface form. Distinct answers might be semantically equivalent, while a small semantic change can turn a concrete answer into an inconcrete one. Uncertainty in the semantic space is therefore generally more informative than uncertainty measured only at the token level. This insight leads to semantic entropy. Semantic entropy moves uncertainty estimation from tokens to meanings. Given a query, SE sample multiple responses, group semantically equivalent answers into class and calculate the Shannon entropy of the resulting cluster probability distribution. If most responses express the same meanings, the distribution is concentrated and uncertainty is low. If they are spread across conflicting meanings, uncertainty is high. This has become an important reference method because different wordings of the same answer are concretely treated as semantically equivalent. However, representing the semantic space with one flat clustering also discards useful information. Semantic entropy uses a binary decision. Two responses either belong to the same cluster or they do not. This creates a single flat portion and overlooks final relationships between semantic communities. Kernel language entropy and semantic graph density model grounded relationships in semantic graphy, but these still do not explicitly represent hierarchical topology. The way small communities combine into broader structures. That hierarchy might distinguish response spaces that look similar under a one-cut partition or a global graph statics. The missing information is therefore the hierarchical organization of semantics. Semantic spaces are often naturally hierarchical. A broader meaning might contain several interpretations, and each interpretation might contain more specific variations. Motivated by compositional similarity, we argue that uncertainty estimation should identify these nested substructures. Two response sets might have similar cluster counts, and global statistics, yet differ in how regularly those clusters are organized. A regular hierarchy can be described compactly, while a discarded hierarchy requires more information. This is the central intuition behind our method. Based on this idea, we propose semantic structural entropy. I will now introduce the formulation of SeSE and explain how it captures hierarchical semantic uncertainty. Let me begin with high-level formulation and theoretical intuition. SeSE is a principled black box EQ framework. It uses sampled responses and their semantic relationships, making it applicable to both open and closed source LLMs. Given a query, we represent sampled responses as a directed semantic graph. The vertices are responses and the weighted edges describe semantic transition relationships. We then convert the graph's organization into an uncertainty score. The theoretical foundation is the minimum description length principle. The best model of that is the one that compresses it most succinctly. We therefore construct a tree-structured hierarchical abstraction that represents the abstract hierarchy of the semantic graph. SeSE measures the uncertainty remaining after optimal compression. Intuitively, it's the minimum number of bits required to describe the hierarchy under random walks. A regular structure needs fewer bits. A fragmented structure needs more. With a single-level abstraction, SeSE recovers the flat uncertainty principle of semantic entropy. Deeper trees generalize it to hierarchical semantic structures. The next example shows why this additional structure changes the uncertainty estimate. The two semantic spaces shown here appear similar at the graph level. Both contain three semantic substracts. A flat method might therefore assign them similar uncertainty. Their hierarchical abstractions are different. For LM1, two fine-grained communities form a regular high-level structure, which admits a compact encoding. For LM2, the relationships are more disordered and resist compression. SeSE consequently assigns low uncertainty to LM1 and higher uncertainty to LM2. In this example, LM1 more consistently supports the conclusion that greening is an excellent solution. The key point is that SeSE does not only count communities, it evaluates how effectively their internal and cross-community relationships can be represented by optimal encoded tree. I will now briefly explain how this hierarchy is constructed. We start with a one-dimensional encoded tree. The root represents the complete semantic space, and every sampled response is a leaf connected directly to the root. We then optimize the tree using two operators, merging groups related sibling nodes into a shared community. Combining introduce an additional abstraction level above related subtrees, allowing broader relationships to be represented. At each iteration, we select the operation that gives the largest decrease in structural entropy. It's accepted only when the decrease is positive. The process stops when no operation can further reduce entropy, or when the tree reaches the maximum height k. The hierarchy is therefore discovered directly from semantic transitions rather than from manually defined labels. The tree optimization stage has a practical complexity of approximately m log n, where n and m are the numbers of vertices and edges. So far, I have focused on shorter responses. Real applications introduce the challenge of long-form generation. Most semantic AQ methods have been evaluated on responses containing only one or two sentences. Real-world outputs are often much longer and may mix correct and incorrect claims. One uncertainty score for the entire response is therefore insufficient. A mostly correct answer may still contain one critical hallucination, while a high response level score does not identify which statement should be questioned. Long-form uncertainty must be both fine-grained and interpretable. We therefore extended SeSE from response level to claim level uncertainty. We first decompose each long response into automatic claims, the smallest symmetric distinct information unions. We then construct a claim response bipartite graph. One side contains the sampled responses, and the other contains their claims. The connections capture fine-grained symmetric dependencies between them. The SeSE of an individual claim is defined through the uncertainty of reaching that claim under random walks. Claims consistently supported across the response space receive lower uncertainty. Weaker supported or contradictory claims receive higher uncertainty. This produces an interpretable score for each claim, enabling a system to highlight the specific parts of a long answer that requires verification. With both formulations established, let us turn to the experiments. The final part presents our short-form and long-form results, followed by our next research direction. I will begin with sentence length generation. This figure summarizes short-form results for 5 LLMs. Each bar is averaged across 5 used datasets. AULC measures how well uncertainty separates correct from incorrect responses. AULC, the area under the rejection accuracy curve, summarizes retained answer accuracy as increasingly uncertainty queries are rejected. Higher is better for both. Across all 5 model settings, SeSE achieves the highest average AULC and AUIC. The advantage is consistent across Llama and Chain families and across model scales. We next examine the more challenging long-form settings. Our long-form benchmark contains 7,407 automatic claims generated by DeepSeek v3.1 and Gemini 3 Flash on FactScore and PopQA. Even these advanced models show substantial hallucination rates, about 28% for DeepSeek v3.1 and 25% for Gemini 3 Flash. Long-form factual reliability therefore remains unresolved. Across all 5 model data combinations, SeSE achieves the highest AULC and AUIC, consistently outperforms described semantic entropy, the strongest baseline. This indicates that the claim response hierarchy provides a useful signal for identifying unreliable claims inside the long generation. The baseline comparison also reveals unimportant findings about model confidence. The verbalized uncertainty baseline, PHVU and ILVU, performs substantially worse than SeSE and discrete semantic entropy. Their weak performance suggests that contemporary LLMs remain overconfident even when their claims are unreliable. Asking a model how confident it is not a dependable substitute for an external uncertainty estimate. This returns us the FLTAL example. Fluent self-confidence can be misleading. As the LLMs evolve into autonomous agents, reliable uncertainty becomes even more urgent. LLMs are rapidly evolving from text generators into autonomous agents that interact with open-world environments. They can make bookings, modify database, call tools, and issue actions that might be costly or difficult to reverse. Here, filter is no longer limited to incorrect sentence. An agent may act before restoring ambiguity, propagate an early error through a long tragedy, or community to an unsafe outcome. It must therefore estimate not only whether a statement is correct, but also whether an action is likely to fail and whether more information should be collected first. Traditional UQ assumes a fixed input and output, whereas agent interactions are dynamic. The operational nature of uncertainty might change during a conversation. What initially appears irreducible may become reducible when the agent asks a clarification questions or observes the environment, and new uncertainty might emerge as the interaction evolves. Our team is now investigating urgent uncertainty quantification, how agents should represent and update uncertainty and use it to decide whether to act, ask, verify, or abstain. We hope this work will contribute to more reliable and transparent AI systems. With that, I would like to conclude. Thank you very much for your attention. If you have any questions, please feel free to contact us.